Now let's introduce average acceleration. In general, acceleration is the rate at which the velocity changes. We can look at average acceleration, which talks about how the velocity changes over a time period, and instantaneous acceleration, which is how the velocity is changing at a specific moment. I want to focus on average acceleration for now. For average acceleration, then, the equation is very similar to what we looked at for average velocity. The average acceleration is the change in velocity over the change in time. If we were to write out those deltas, because remember that triangle is the Greek letter delta, and that delta V over delta T can be rewritten in terms of the initial and final values. If I take a look at my equation, what I see is that I can figure out my dimensions for acceleration by looking at the dimensions of velocity, which are length over time, the dimension of time, which is just time, and that gives me that it's length per time squared for my dimensions for acceleration. That means it has a standard metric unit of meters per second squared, but you might also see it written out in a few different formats, where these first two are actually identical units but written out slightly differently. And this last one is miles per hour per second. It's not our standard unit, but it's still an acceptable unit because it is a length per time divided by a time. So now we get to a quick example. In this case, we've got a ball starting from rest, which reaches a velocity of 10 meters per second in 4 seconds. Well, from our problem, we have two knowns that we're given that we see right away, the time and a velocity. And if you read the words in the problem, we see that this is the final velocity. Our initial velocity wasn't given as a number, but it says starts from rest. So that means our initial velocity is 0. Working that into our equation, we see that we've got 10 meters per second divided by 4 seconds, or 2.5 meters per second squared for our acceleration. Here's a second example, which is very, very similar. A ball rolling at a velocity of 10 meters per second comes to rest in 4 seconds. Again, we're given a couple of knowns, but in this case, the velocity is the initial velocity. And from the words in the problem, we see that it's the final velocity, which is 0 meters per second. Plugging those into our problem, what we see here is that since it was having a decrease in the velocity, I've got minus 10 meters per second divided by 4 seconds, so that gives me minus 2.5 meters per second squared. If I think about what this average acceleration means on a graph, it's very similar to what we saw for average velocity, where we had the position versus time graph. Now we have a velocity per time graph. But my equation for the average acceleration still depends on me seeing I've got 2 points, what's the time span between those 2 points, what's the change in velocity for those 2 points, and then the slope of the line connecting those 2 points is equal to the average velocity, the change in velocity over time. Now if I take that same graph and those same points, what I see is that my change in velocity is going from 1 second to 6 seconds. My change in velocity is going from 3 meters per second to 6 meters per second. So I could use the form of the equation for average velocity using my initial and final point.